Okay, so now that we have that under our belts, we're going to go ahead and solve this differential equation. So we've already established that this right here is our n, and that this right here is our m. So what we're needing to do now is we need to find psi. Find psi, because if we find psi, then we're done. We're almost done. We just have to substitute it into the left-hand side and equate it to an arbitrary constant and solve for y. Okay, well let's think about what this means. So n we said is the derivative of psi with respect to t. I'm sorry, with respect to t, yeah. So n is the derivative of psi with respect to t. That means that if that's the case, then the derivative of psi with respect to t is equal to 2t plus y squared. Well, I can solve for psi in this equation by integrating both sides with respect to t. Now, to carry out this integral, we might say to ourselves, well, we can't do this because the right-hand side depends on y, which is a function of t. But here's the thing. With respect to psi, for the function psi, t and y are both independent variables. So because of this, I can treat one or the other as constant. So therefore, when I take the integral of d psi dt with respect to t, well, that's just the integral of the derivative of psi, and therefore that will just produce psi, and the derivative of 2t is t squared, the integral of y squared. Okay, so with the integral of y squared, because we're treating y as a constant, so let's think about what would happen if you integrated, for example, 3 dx. Well, you would get 3x. Plus some constant, potentially. Plus some constant. Therefore, the integral of y squared, because we're treating it as a constant, is going to be y squared t. So this, again, this is just some constant right now because we're holding it fixed. Now, normally we would just say that there's some arbitrary constant here. But let's think about, with partial derivatives, what might have gone away when we took the derivative with respect to t. So when I, as an example, take the partial of, say, x squared plus y squared, then if I'm holding y constant, then the derivative of y is 0. So we're treating y squared as if it were a constant. Therefore, this constant here may have involved numbers, like, this could have been x squared plus y squared plus 17, and the derivative of both y squared and 17 would be 0, so we would just end up with 2x as that derivative. So this is not necessarily just a constant, this is potentially some function of y. And I can check my work. If I take the derivative of t squared, I get 2t, if I'm taking the derivative with respect to t. If I take the derivative of y squared t with respect to t, I get y squared. And if I take the derivative of some function, like here, this could be considered h of y, the derivative of that whole thing is 0, and therefore our psi function matches up. Now, we don't know what this h of y can be. But here, let's do the same thing for m. M is the derivative of psi, but with respect to y. So that means that if I take the integral of d psi dy with respect to y, right, because this is the derivative with respect to y of psi, and this is the integral. Therefore, that's just going to produce psi. And now I need to integrate the right-hand side of what m is, which is 2ty. And that's going to be with respect to y. So, okay, well, let's see here. So that means 2 and t are both constants, so I can factor that out. And the integral of y dy is equal to 1/2 y squared. So if that's 1/2 y squared, the 2 and the 1/2 will cancel out, and I'll get t ty squared. Oops. And now let's think about what could have gone away when we took the derivative of psi with respect to y. Well, when we take the derivative with respect to y, any function of t will have gone away. So if I take the derivative of psi with respect to y, the derivative of g of t will be 0. And this could again be something like t squared plus 7, or any function involving a constant and being only that of a function of t. All right, so this one poses kind of some issues, right? We said that here we have psi is equal to this, but down below we're now saying that psi is also equal to this. So how do we reconcile the difference between those functions? Well, let me write them side by side. So we'll just say candidates for psi. So we have t squared. Let me write it like this. So the first side that we have here is ty squared plus t squared plus h of y. Right? And we know that these two are the same side. These guys have to be the same function. So that means if I compare it to the second one, well, they almost are the same function. Here we're good. They match in the first term. But then there's plus a g of t. So the only way for these two equations to be the same is for, well, those two terms are the same. That means g of t, it can only be some function of t. Therefore, if it has to match the first equation, g of t must be t squared. And then what does h of y have to be? Well, I don't have any function of y in this equation here, but I do know that it's totally okay to write plus 0. And therefore, I can now argue and conclude that h of y is equal to 0. And so I can write that psi of t comma y is equal to ty squared plus t squared. And that is my final psi function. So, in its totality, what do we have now? Well, we found this function that, according to all of our substitutions, the solution to this differential equation right here is, if we could find that function psi, then psi equals c is the solution. So that means our solution to the ODE, solution to our original ODE, which is the 2t plus y squared, plus 2ty y prime equals 0, is psi of t y equals an arbitrary constant, which means ty squared plus t squared equals the constant. And finally, I can solve this for y. I can see that if I subtract t squared, I'll have ty squared equals c minus t squared. Divide both sides by t. We get c minus t squared over t. And finally, take the square root of both sides, so we have y equals plus or minus square root of c minus t squared over t. Now we can check our work, just like we always have been able to. We could take the derivative of y, substitute in this whole mess for y, and then take the derivative and plug that in for y prime and show that that left-hand side cancels out and produces 0.